lesson 2.1, I went over the composite function. In lesson 2.2, I'm going to go over one-to-one functions and inverse functions. Keep in mind, a function is such that for every x, there is just one value of y. So examples of functions would be your slanted lines, your horizontal lines, your typical polynomials, for example, parabolas that open up or open down. A parabola that opens sideways would not be a function because a vertical line would cross that graph at more than 1 point. So typically for functions, a vertical line has to cross the graph at 1 point only. Otherwise, it's not a function. Now in this lesson, I want to focus on what is called a one-to-one function. So here's your definition. A function is one-to-one if for x1, x sub 1, and x sub 2, and x sub 1 and x sub 2 here are different values in the domain of f. So if that's the case, then f of x sub 1 cannot equal f of x sub 2. That is, the y values corresponding to those x's cannot equal. Another way to say this is for every y, there has to be one value of x. So an example would be, let me just look at your parabola. Okay, the drawing's kind of bad here, but let's assume this is a nice symmetrical parabola along the symmetric with respect to the y-axis. If I pick a point over here, go, let's see, -1, and if I go over here to the right, +1, and let's say this is the graph of y equal x squared. Then if I go 1 unit here, up here, then this would be the point 1 and 1. Okay, if I go on the negative side and then go find the point right here, so -1 squared is 1. So this point over here, opposite that other point, is a point -1 and 1. Okay, this parabola is a function. For every x, there is just one value of y. A vertical line crosses the graph at 1 point. But notice that when y is equal to 1, for this point is 1, 1. Over here, this point opposite that is -1, 1. So when y is equal to 1, the x value can be 1 or -1. Okay, so this is not a one-to-one function. To be one-to-one for every y, there has to be one value of x. So a vertical line crosses a graph at 1 point, means it's a function. Now if a horizontal line crosses the graph at only 1 point, then it's one-to-one. If a horizontal line crosses the graph at 2 or more points, then it's not one-to-one. Okay, so that's why we have the horizontal line test for one-to-one functions. For a one-to-one function, a horizontal line has to cross the graph, no matter where you draw it, has to cross the graph at just 1 point. Okay, now here's the next definition. If a function f is one-to-one, then it has an inverse function. Okay, so if it's one-to-one, it has an inverse function denoted by f inverse. So f to the -1 is read f inverse, and such that if the ordered pair xy belongs to f, then the ordered pair yx has to belong to the inverse. Okay, so it's such that xy belongs to f if and only if yx belongs to the inverse. In addition, this is going to be true. F composition the inverse, or f inverse composition f, always equals to x. Now you can look at the last video, 2.1, the last example that I did. I referenced that those two functions that I worked in that example were inverses of each other. So I did this calculation and I got x. So you can look at that as an example. The other thing we need to know is that the line given by y equal x is the line of symmetry for the graphs of y equal f of x and y equal f inverse of x. So that means then that if I sketch the graph, okay, let's suppose that's the point 0, 1, and I'm going to sketch the graph of what is called an exponential. Okay, so I missed the point here, but let's suppose that it's right there. Okay, so let's suppose that's the point 0, 1 right there. So let's call this f. Okay, the line y equal x, that's the line of symmetry. So what that means is if I take this graph and reflect it over that line, I get the inverse. Okay, so if I reflect this over the line, so if the graph passes through 0, 1 here, remember what I said in the last video, if you have a function and its inverse, the ordered pairs of 1, if you reverse the ordered pairs, those ordered pairs will be in the graph of the inverse. So if the graph passes through 0, 1, f passes through 0, 1, then f inverse will pass through 1, 0. So the inverse would look something like this. Okay, and this would be, and I apologize for the graph in here, but it's a little bit difficult with this tool that I have here. But so basically, I reflect this over this. So this is more. Let me do it. It goes something like this through there, and then it comes like this. So this is just reflected over the line. So this is f, and this would be f inverse. So anytime you have the graph of a function, you can reflect it over the line y equal x, and you get the graph of the inverse, and vice versa. Okay. Now, let's clear this. And let's look at some examples. Okay, so some basic examples which will apply the definitions that we went over. So it's determine whether the function 2, 3, okay, so in this case it just gives you the ordered pairs, so it's very basic. Determine whether the function consisting of 2, 3, negative 1, 5, and 8, 3. So this would just be 3 isolated points. It's 1 to 1. Okay, so again, in order to be a 1-to-1 function, it has to be a function. So for every x, there has to be one value of y. Okay, when x is 2, y can only be 3. When x is negative 1, y can only be 5. When x is 8, y can only be 3. So this is a function. Now, is it 1 to 1? Okay, to be 1 to 1, when y, for every y, there has to be one value of x. Well, notice when y is 3, you see a 3 here and a 3 here. So when y is 3, x can be 8, or from this one, x can be 2. Okay. So for this one, the answer is no. This is not 1 to 1. Okay. Number 2. Find the inverse of the 1-to-1 function. Okay, so if you're given ordered pairs and you want to find the inverse based on what we talked about in the definition, you simply reverse the ordered pairs. So the inverse will simply be those same ordered pairs, you just reverse them. So if you do that, you're going to get this. Negative 1, 2, 2, 3, 3, 1, 0, 5. Now I want you to keep in mind that because you do that, the domain of the function, okay, in this case the domain of this function consists of 2, 3, 1, and 5. The domain of the function is the same as the range of the inverse, okay? Because remember, the domain is given by the x values. The range is given by the y value. So if I ask you, what is the domain of this function, you would write out a set and you would list 2, 3, 1, 5. if I said what is the range, again you write a set and you list -1, comma 2, comma 3, comma 0. Okay, over here it's just reversed. So if I ask you what is the domain of the inverse, and you would write the set -1, comma 2, comma 3, comma 0. And the range is 2, comma 3, comma 1, comma 5. Okay, because you switch the ordered pairs. Anyway, in this case, they're just asking for the inverse, so there it is. You just reverse the ordered pairs. Okay. Now for this one, it's kind of like the one I just did a while ago. For the graph shown, draw the graph of the inverse. Okay, so there you have it. So this is again looks similar to an exponential. Okay, so again, like I did a while ago, if this is the point, say 0, 1 here, if this is 0, 1, then the graph would have to pass through 1, 0. So it would have to pass through this point over here, and then it would just be reflected over that line. And go something like this. Okay, so this would be your f right here, and this would be the graph of the inverse. Okay, now in the next lesson, I'll be looking at exponential functions. Okay, so an exponential function has a graph that looks something like f. And then in the lesson after that, I'm going to be looking at logarithmic functions, and they'll have graphs something like what I have here for f inverse. So basically what I'm telling you is that the exponential function and the logarithmic function are inverses of each other. So if I take the ordered pairs of one and reverse them, I get the other. Okay, but anyways, in this case, we're just using the idea that the line y equal x is the line of symmetry for a function and its inverse. So this is what you would have. Okay. Now, for the next one, we have the function f of x is equal to x squared minus 2. Okay, so this is a parabola with vertex at 0, -2, and because it says x greater than or equal to 0, basically they're giving you the domain. They're giving you the domain of this. Okay, that's your domain. So if I were to draw the graph of this, okay, this is what it would look like. So it would have vertex at 0, -2, so I go down 2 units, and then because the coefficient here is positive, it opens up. So this would be a parabola that opens up, so it would go something like this. Okay, now this side, so normally the parabola goes up on this side, and then on this side it goes up. Now the reason I don't have the left side here is because the domain is restricted to x greater than or equal to 0, so I only have half the parabola. Okay, and because we're finding inverses, if I include the left side, that would not be a one-to-one function. Okay, so I only want one-to-one functions because one-to-one functions have inverse functions. Okay, one-to-one functions have inverse functions, but if they're not one-to-one, they're still going to have inverses, but they're not going to be functions. For example, a parabola that opens up is a function, but it's not one-to-one. Now it does have an inverse. What do you get if you find the inverse of a parabola that opens up? Well, you get a parabola that opens to the side, say to the right or to the left, depending on the coefficient of the square term. But a parabola that opens sideways is not a function because a vertical line crosses a graph at more than one point. Okay, So here we're interested in inverse functions. So in order to get an inverse function, the original function has to be 1 to 1. Okay, so this is what we have. Okay, so in this one it says find f inverse and state the domain and range of both functions and graph the functions as well as the line y equal x. Okay, well there's a line y equal x. Now I'm going to graph this. This would be f. This would be f. Okay, now to get the graph of the inverse, I would reflect this over the line. Okay, so this one passes through 0, -2, so the inverse should pass by reversing the ordered pairs through -2, 0. So it should pass through this point right here. So if I reflect this over, I get this, and then reflect this over, I get this. Okay, so basically, this graph is going to go something like this. Okay, a little bit off here, but it goes like this here, and then actually should be more like this over here. Okay, so I'm a little bit off here. Let me try this again here. So let me just erase this. Okay, so let's see. Well, I'm still a little off, but anyway. Let me try it again. Okay, something like that. Okay. This thing would be f inverse. Okay. So if I look at f, the domain of f is x is greater than or equal to 0, which is this right here, because it's just to the right over here. So x, and of course that's given, x greater than or equal to 0. The range goes from -2. Okay, so the range of f, okay, this is r sub f, range of f, starts at -2 and then it goes up. So it's from -2 to infinity. So keep in mind that the domain of the function is the same thing as the range of the inverse, and the range of the function is the same thing as the domain of the inverse. Okay, so that's why we have this. Domain of f is equal to the range of f inverse, which is 0 to infinity. So from 0 to infinity, 0 included. The range of f is the same thing as the domain of the inverse of the function, and that goes from -2, including -2, to infinity. Okay, so this one again goes up like this. Okay, so the domain starts at -2 for the inverse, it continues to the right, and the range starts at 0 and then it goes up, in this case like this. And there you have it. Okay, so these are the graphs, and these are the respective domains and ranges for both of those. Now I need to also find f inverse. Okay, so to find f inverse, I'm going to take this right here, f of x equal to x squared minus 2, and I'm going to interchange the x and the y. Okay, so basically this right here, this f of x, that's my y. So I'm going to interchange the x and the y. So where I have a y, I'm going to put an x. Okay, so this will be x over here, and then where I have an x, I'm going to put a y. Okay, so this will be y squared minus 2. Now, by interchanging the x and the y, that has the effect of reversing the ordered pairs. Okay, so that's how we get the inverse. Then I just solve this for y. So this will be x plus 2 is equal to y squared. Okay, so then I take the square root of both sides here, so y then is equal to plus or minus the square root of x plus 2. Okay. Plus or minus the square root of x plus 2. But since I know that the range of the inverse goes from 0 to infinity, then I know that this has to be positive. This has to be positive. Okay, so this then, I could rewrite it in functional notation. This would be f inverse of x. And this would equal to the square root of x plus 2. Okay, so here you have your domain and ranges for the respective functions. And then here you have the computed inverse of the function. F inverse of x is equal to the square root of x plus 2. Okay, so this concludes this video. In the next video we'll be looking at exponential functions. So again, any suggestions, please post them. And these are helping you. Please subscribe to the channel. We'll see you in the next video.